Good afternoon. Last year, I introduced to this group at PM Summit 2017 a group of new interconnects that had just appeared, just gone public with 3 different consortia in November of 2016. There was a lot of interest in that talk. So this year, we've brought in experts on each of the 3. So first, we're going to hear from David Koenen from ARM, who will talk about CCIX.
Thank you very much, Doug. My name's Dave Koenen. I'm a senior product manager at ARM. And it's not the ARMpire that Stephen might have alluded to. I think of it more of the CCIX being more of the Rebel Alliance, kind of because it turns out better for them at the end. So what is C6? C6 is essentially a new class of interconnect. That's the way a fabric, or it could be a fabric on a PCI Express interface. But its mission is primarily to provide an interface for accelerators, GPU accelerators, and many different others, to have a cache-coherent interface rather than doing a typical DMA or a non-coherent DMA or some other kind of DMA instead. And just to help transfer of memory and to use cache-coherent mechanisms for victims and reads and writes, and having that memory go back and forth. So a consortium you can work across switches and others, and it's really an industry standard that we're trying to get moving forward. Now the consortium is now comprised of 42 different members, incorporated about 2 years ago, became more public about a year ago, I talked about. It's mostly a hardware specification, but we also have a guide for UFI and BIOS developers, how to write and discover C6 devices on PCI interfaces. One of the hardest parts about getting all these members together is to agree on the interfaces and the protocols and the transaction layer and the error handling and the exception handling on the end nodes. I mean, yeah, they eventually came up with the transactions that go across the PCI bus, but just discovering and having all those many companies agree to have their own cache coherency policies, now agree to a common set of cache coherency policies and discover them and work across them was really challenging and difficult. It was one of the larger specs in going as compared to just the transactions that go across that interface. So it's been a lot of work, and we got to the 1.0 spec, and we're currently working on finishing up the BIOS specification, but there's still more work to be done and still more members joining. So let me talk about some typical examples of topologies that C6. Again, it's more of an interconnect then. So a direct processor to accelerator interfaces for accelerators like GPUs, encryption engines, also neural networks to machine learning or computer vision to have a cache-coherent interface to those. You talk directly to them. Memory can exist on those. You can have SRAM or DRAM on those accelerators as well that the processor can access, or vice versa. So you can have the accelerator access the SoC, the processor's memory, or the processor access the accelerator's memory, or vice versa. We'll also have showing an example for this persistent memory forum is having a device out there that just have memory out there, a block of memory that sits on the interface out there. You can scale the interface or the PCI lanes for that, for the bandwidth appropriate for that memory technology. Or it can mix them, going across a standard PCI Express type switch to have both accelerators or several accelerators, several GPUs, or having direct connects to them, and combine with memory. So instead of using the DRAM on there, you can go to memory, and all 3 devices can access them if they're all cache coherent and they all have access to them. Other than that, you can create specialized systems where you have each of those processors have maybe a very low latency cache coherent interface between for inter-processor communication between the processors, and still use C6 to accelerators, or a mix of C6 accelerators and PCI Express devices you connect with PCI Express, but on the, like an MCM module where you have a bunch of devices that want to talk coherently to each other, having them talk C6, but still have the legacy PCI Express on there. These are just some of the examples. There's more. You can do daisy chain, mesh, switch topologies. It just supports a lot of different topologies depending on the configuration. And within that memory example, say we have an ARM SoC with like DDR4 memory on it, and you would generally connect to one of the cross points on the mesh and have choice of either going PCI Express at first and then eventually C6 when it's discovered that way. It starts off at PCI Express. You do the normal PCI Express discovery in BIOS, and you discover that with the designated vendor-specific extension capabilities that there is a C6 capable device out here, and then you load the appropriate software library to talk to that. You map that memory into a region of memory, and now you have, once it boots up, you have access to this new memory area that's cacheable. And you can get to it and make it cacheable, and you can have victim line writes from the core processor into this memory, and so forth. For those who have already developed NVMe type devices or NVMe memory controllers out there, think of now adding a C6 layer to it. So now you can have PMEM access across that to be able to access that memory directly, in addition to having your typical block storage type transfers. You can have memory byte level transfer, cache line type transfers as well. So some of those things, talking about shared virtual memory space, driverless. For the memory controller aspects, yeah, you can be driverless. Basically, you're just discovering that it's a memory device, and you're mapping that region into the OS, and you're saying that, okay, it's cacheable. Yes, it may take a little longer. Maybe you want to have different properties of that, saying it's a little longer, but it can be treated like a NUMA type memory instead. And also enabled, it's just memory. So you can just access it just like memory before. And another advantage is that you can use it, you can use the same PCI Express pins on the SoC and on the PCI Express device to be PCI Express or C6. You use the same traces, you use the same connectors as PCI Express, or you can have for embedded systems having direct connect and not having to use any of that. Minimal OS changes. You don't necessarily have to have a driver. You can just map it. You may want to have a UFI driver to say you want to configure it and partition it up and say I want the memory for this type of VMs or so forth, and break it up that way, or give properties to that with a UFI initialization driving and configure it and everything. But once it's booted and running, it's just memory, and you can then load software libraries to manage that thing, and instead of having, and also like getting new updates to the accelerator firmware for if it's an accelerator, and having that loaded and rebooted onto the accelerator. So there's many, many advantages of doing this in the software firmware capabilities of having those. It also supports a virtualization capability. So you can just treat it, again, it's just to treat it like memory, and you can break up that device and supporting virtualized memory as well. We have a test vehicle coming in the form of both an SoC and a board with a combo PCI Express and C6 slot. That's the red slot over there on the end. And we've been working with Cadence and TSMC and Xilinx on this. Cadence is providing the PCI Express and the C6 controller. TSMC is a 7 nanometer part for the ARM SoC that has the C6 and PCI Express interfaces on it. Xilinx has an FPGA, IO FPGA for doing a lot of the typical IO stuff that we have to connect to. And we plan to have this probably by the end of this year coming out for testing out. 2 memory controllers on it for DDR4 memory. And it's probably one of the world's first C6. Well, I know there was a demonstration by Xilinx for a NIC accelerator at the Supercompute 17 showing accelerations for layer 2 forwarding through that. But this is going to be a first like a SoC based with C6, and it's a demonstration vehicle. We're just making a few hundred of those. We're not in the chip selling business at ARM, or the ARM Empire isn't. So to conclude on this, the benefits are that you can accelerate applications for things like machine learning, for smart NICs, and analytics. You can add memory to each PCI slot, and you can access it in byte level and cache level access. You can work across existing PCI Express interfaces and then upgrade your SoCs and upgrade your endpoints to be cache coherent, whether it be an accelerator or a GPU accelerator or encryption accelerator or whatever. It just uses shared virtual memory space, and it's easier for the developers and software developers to just write to it instead of, and doesn't have to use a typical OS I/O driver, and it just uses the memory to talk to it back and forth. And that's it for me. I'm going to now hand it over to Jeff from IBM.
Hello, so I'm Jeff. I work for IBM, though I think I might be here under the guise of OpenCAPI Consortium, so I should be speaking beyond just my employer. But yeah, so I'm from Austin, Texas. My name didn't make it up here, so Jeff Stukley, it's in the session things. So I'm going to talk about OpenCAPI. The name is maybe worth a few bars to explain what it is. We created a coherent attach, I guess you could say somewhat similar to what the C6 people had done back in 2014, but across the top of PCIe. So we built a layer strictly tunneled through PCIe, and that was called CAPI. CAPI was Coherent Accelerator Processor Interface. That was great, but then we said, well, we didn't like the burdens of PCIe from a latency perspective in particular. And also we can put higher efficiency chip interfaces if we run dedicated 25 gig signaling. So we said we need to do something new, and our marketing people really liked that we'd spent a lot of effort on CAPI, and so this was open, and so now it's called OpenCAPI. So anyway, that's what OpenCAPI is all about. The open part being that it's no longer associated with just IBM products. This is an open standard to work in a variety of systems. So what are we accomplishing with OpenCAPI? It's beyond memory. It's really a continuum from local traditional DRAM attached memory up to other devices such as storage or accelerators. We'll eventually support coherent accelerators. So we'll be able to do cache coherence across the host processor up to accelerators. At this point in time, though, we actually don't have full coherence. It's more of a traditional PCIe DMA type model where you can move data in and out of host memory similar in the ways you could with PCIe. But the key point here, I kind of wrote, try to keep things fairly simple here since we only have 10 minutes. What are the attributes of OpenCAPI that sort of drive the design? The first one is we needed to achieve very low latency and high bandwidth. And we're doing that in a way that's tightly coupled to the host silicon. And so you'll see things like in C6 or in Gen-Z where there's switching capability and more elaborate ways to build more complex systems. What we did is we have a very tight coupling between the host silicon and the processor. So everything is intended to be directly connected, which enables us to have a very streamlined low latency protocol. And also if you talk about things like coherence, coherence is obviously very tricky to get right and to not have failures out, in a year after you ship the box. I've been doing coherence for, 20 years or so, so I have scar tissue there. So it's really hard to do coherence without tight coupling. When you start to think about the number of virtual channels required to build proper coherent interfaces, and then to take those virtual channels across switches, you end up with kind of an untenable level of complexity. And so a couple things here. Coherence is hard to do across switches. We also want to be able to achieve very low latency with our devices. Broad range of devices, I kind of already talked about that. And something else that's maybe unique to this protocol is we're calling it an asymmetric protocol. So the responsibilities of the host silicon are different than the responsibilities of the attached devices. And so what we wanted to accomplish here was to do more work in our host silicon to make the devices simpler. If we're going to be successful here, we want to have a small number of host vendors, right? We're not going to have 15 different host microprocessors, but we may want to have a large variety of attached silicon. And so things like address translation are very much contained with the processor. Even coherence itself is very much managed within the bridge that sits on the host silicon, and that exposes the accelerator only to a very simple, messy protocol, rather than the more complex states you typically find within coherence. It also gives us a fair amount of security and isolation. So for example, we have a full checkout directory of everything that's cached in the accelerator. So if the accelerator were to fail for some reason, we know exactly what lines they might have cached in modified state, and therefore the system can recover. So this is very important if you want to have redundant I/O devices. You can't really have a device crash the system. And so we believe this is unique compared to FPGA attaches using QPI, for example, which people have used over the years. I guess it's not called QPI anymore, but if a device crashes there, the coherence protocol didn't keep track of the other host silicon, what was cached, and so the whole system has to go down. And so we need to be able to build network devices that have redundancy to give us resilient systems, and so we really have to be very careful about how well we sandbox the accelerator. So the accelerator has a big sandbox, it sits in a sandbox. It also is designed to be a simple protocol compared to the more complex coherence protocols we have. So I like talking about this here. I decided to put this chart in. This is kind of new. And so where did OpenCAPI come from? It came from two places. It came from CAPI, PCIe-based approaches. But it really also came from our memory attached we have on our POWER8-based servers. So POWER8 is our kind of previously designed system. Came out around 2014. And what we did in POWER8, and I think this is a pretty impressive accomplishment, is we took our processor and we used differential signaling. This particular system ran at 9.6 gig. Today we're at 25 gig. But so 9.6 differential signaling, talked to a memory buffer chip, which had a 16 megabyte cache on it and 4 DDR ports. And so this chip would sit on the DIMM. It's a fairly big chip. The DIMMs were fairly big. But we were able to essentially connect 32 DDR channels into one processor silicon with pretty efficient interfaces. The silicon area for differential signaling is tremendously less than DDR5s. And so we were able to build this interface to let us have essentially an intermediate memory buffer. So why did we do that? Back even in 2014, we had visions of these new emerging memories that people are talking about in here. And when this interface is built, we call it an agnostic interface, right? It's not like DDR where there's a deterministic latency. You send a read operation out, and then this could be any type of media you want it to be. That said, we still don't really have viable media beyond DRAM, so we never built any of these other buffers. But the ideas of building a low latency attach are certainly here today. And this is something we're pretty proud of. So our direct attach memory, if we would have built a direct attach controller, we'd have about 70 nanoseconds of load-to-use latency. With the optimizations we've been developing in buffered memory really for several generations, we achieved 80 nanoseconds. So the penalty of going through the differential signaling and through this buffer chip was only about 10 nanoseconds. And this is something we did in 2014. I went and looked up the number for a certain Evil Empire chip that had a very similar design, and they were at 126 nanoseconds. So their direct attach solution was 72 nanoseconds, and then they had 26. Hopefully I said the same number twice. I just looked it up. So this isn't necessarily easy. There's a lot of tricks we have accomplished to make this happen. So what were the problems with this? It was proprietary. We tried to get some other memory vendors to build other types of memory solutions with it. The memory wasn't available, and they're also, hey, this is only for IBM systems, so why would I want to do that? It also had some issues where the lane widths were non-standard. It made us hard to get connectors. So we wanted to go to something more standard. For today, for OpenCAPI, for example, we have by 8 lanes. And it only gave us the ability to just return data as a slave. So as we look at some of the more sophisticated protocols, we want to enable accelerators to do DMA-like protocols. So what you can essentially, what we did here is we took our latency optimized solutions we developed here, and then we extended it to be the functionality of our coherent accelerator with CAPI. So we kind of combine those two things together. So what types of memory protocols are we trying to accomplish? We want to be able to do traditional DRAM attach with very little latency overhead. By the way, we think we can take that 10 nanoseconds down to about 5 nanoseconds. Keep in mind that 10 nanosecond had a 16 megabyte cache lookup and a mux into 4 different DDR ports. So we think a very small, thin buffer that only has 1 DDR port, we can achieve about a 5 nanosecond adder over a traditional memory. Which once you have any reasonable level of utilization, your loaded latency is actually less with this solution because you're able to have that much more bandwidth behind the device. We also want to be able to directly attach through the same processor pins storage class memory, emerging memory technologies. Right? This interface out of the host silicon, we want to be able to pull out a DIMM that has DRAM on it, plug in a new DIMM that has some other memory solution. This is enabled by having non-deterministic latency, so it's a fully tagged read as opposed to DRAM interfaces that have a deterministic interface. And tiering is also very important, and this is one of the reasons we want to have very low latency, because you could put some of the storage class memory, but that could be daisy-chained behind traditional DRAM through accelerators, right? So I could have DRAM on a card that then talks to storage class memory as caching models or potentially just different mappings. So this lets us use all of our pin silicon to have DRAM and then put a layer behind it of the higher latency storage class memory. So we see all three of these approaches as being viable and important. And we get a lot of flexibility because this is differential 25 gig signaling. We can actually run it across cables that are fairly long. I think our Molex guys did a 2.5 meter cable. The typical one we're doing is only 12 inches. But you can essentially take your host silicon, drive this 25 gig signaling out to memory drawers, inside the box, outside the box. So where are we at today, though? Here's our POWER9 chip. It kind of looks like Space Invaders is what I think. The last one looked like, anyway, Space Invaders. So we got 25 gig. Coming out of here, we have 32 lanes. These are all by 8 interfaces. When you look at the OpenCAPI spec, you'll see things like 25 gig and by 8. It isn't that we don't expect it to go on higher frequency or wider interfaces, but that's what we actually have today. So this is a product we just started selling. So this is something that's in the market today. Bandwidth, we're measuring 25 gig of a by 8 turns into 25 gig peak, and we're getting about 22 bandwidth. The other thing that I think is very interesting is we have a Xilinx FPGA connected to this, and we're running it at 400 megahertz on the Xilinx FPGA. We're able to achieve 80 nanoseconds of the DL-TL transceiver send-receive inside the FPGA. That's I talked about 10 nanoseconds, that was custom silicon, but even with FPGA LUTs, we're getting 80 nanoseconds in the device. The thing that's interesting is their hard IP PCIe equivalent is 400 to 500 nanoseconds. So you can see how the optimizations we put in the protocol, even with LUTs, enable us to get to about 80 nanoseconds. Right? We made the protocol require very little decode, no byte rotations, to where you can essentially take data straight off the interface and operate on it. And actually, this one isn't the most optimized solution we can have. We can actually take this down to about 60 nanoseconds if we speculate that the CRC is good. So the protocol is designed to where you can start interpreting data and know where the right data is going to be even before you've checked the CRC. So speculating, that gets some jokes, by the way, when I say speculation's got a bad name. I won't say anything more about that. But speculation in a good way, not the bad kind. We have a big consortium. I think these charts will be posted. We're developing this in an open way. We've got a pretty broad set of people on the kind of key contributors. This is on the next slide. We have a website, opencapi.org. It's been out there for about a year or so. I will talk to this one on people who are actively doing things. So we have our POWER9-based systems that support OpenCAPI. Mellanox has a network card that has a Xilinx FPGA on it. So you can think about that as they have the ASIC NIC, and then they have next to it, they have an FPGA. And so this is kind of a packet processing type device. We have cards with Xilinx FPGAs as well. Molex is building this thing they call the FSA, which is a pretty interesting device where they take an FPGA that's OpenCAPI attached, a Xilinx FPGA, It's OpenCAPI attached to the processor, and then they have a large array of NVMe drives. And this enables somebody to connect NVMe drives through low overhead, non-device driver, load store model type optimizations. So that's kind of what the immediate hardware solutions we have are. So going forward, we're going to have new versions of our power processor that supports a broader set of devices, and we also have some silicon stuff that's in the works from other vendors going forward. So I think that covers it all, and we'll do questions at the end. And Gen-Z.
Mike Krause, I'm the lead architect for Gen-Z within the Gen-Z Consortium. So I'm doing more of a memory focus in this talk. Gen-Z can actually do quite a few things. It's designed from the start to be a memory-centric, memory semantic communications paradigm. So everything's been designed by recognizing everything we do in the world, all the different protocols we created in that really come down to reading and writing data. So we tried to simplify and distill it down. There's quite a bit of things in here. I'm not going to go through it, but the key things are it is designed for very high performance, very low latency. It is designed for reliability, no stranded memory, lots of ways to build highly reliable memory subsystems, highly scalable subsystems. For example, memory interleaving out to like 64 nodes. So you can take some of your SCM modules, maybe they're at 10 gigabytes a second. If you really wanted to scale them out, you could get 640 gigabytes a second out of it. We have built-in security, and one of the things actually we're going to be adding, our 1.0 spec is just about to go public right now, but we're going to be adding actually data encryption and authentication into the architecture because we've all seen Spectre and Meltdown and all the other things going on. So we've built security in from the start. We're going to take it to the next level now. And extremely flexible, and again, we have a lot of compatibility with existing OSs, but for everybody in Linux, they kept telling me, stop saying you don't need any OS mods because in Linux we like to do OS mods. So there are a bunch of people in Linux who are trying to do and take advantage of Gen-Z's capabilities. But in theory, you slide it in, memory looks like memory, looks like it's DDR memory, doesn't matter. And then finally, it's designed to really be economical and focus on the OpEx. So from a memory perspective, again, we can slide in. We slide in under an MMU, just like you would have in a system. You map it in, similar to what David was talking about. But once you get the address program, system firmware brings that in. You actually don't need any UEFI changes, ACPI changes. Any of the base infrastructure doesn't need to change. System firmware basically deals with this topic. But once it's mapped, you can just do load stores. And it's completely memory media agnostic. So whether it's a nanotube version, a ReRAM, I don't care what it is. There's a set of abstracted things that we communicate up to give you the properties of the memory. Like, what is its latency? There are ways to inform you about endurance. The architecture has a bunch of stuff built in to say when things are going bad. You know, you can support row remapping, sparing devices, all sorts of stuff is communicated up. So you can now support a variety of different medias, and in fact, different generations of the same media, which is something people don't talk about a lot, but actually that does make a difference for anybody involved in medias. And you can do that without having to change your software at all. We support two different physical layers. We support the PCI Express physical layer. That's the 16 gigatransfer. We also support the 802.3 electrical. That scales up to 112. That's where IEEE is going. So we actually can have modules that go from 32 gigabytes a second to 400 gigabytes a second per module. And one of the things I like to point out to people is people always talk about, DDR is going to last forever and all that, and it's done a really great job. I remember when DDR4 was being done, there'll be no DDR5. Well, now we have a DDR5. But if you look at the roadmap for DDR5, it's about 400 gigabytes a second payload in terms of performance out of it in the 2022 timeframe. In this time frame now, we're seeing more and more co-packaged announcements. You just saw Samsung made a big announcement the other day for supporting high bandwidth memory. So these are systems that are going to have terabytes a second of memory bandwidth, and the question is, how do you get in and out efficiently? And that's one of the things we anticipated from the start. How can we do this? We support a variety of different topologies, different capacities. We can do co-packaged memory, point-to-point, mesh, switch, et cetera. You can scale this within the box, outside the box, even within the same package. From a persistent memory, since this is the persistent memory capability thing, we support logical PCI devices that allow us to do block semantics out to like 8K devices fairly trivially. kind of breaks past the limits of PCI Express itself. But from a persistent memory perspective alone, we have a whole series, and you can see the operations that are supported that you can do on a per operations basis, whether it's poison, partial, full cache line, 256-byte payloads, whatever you want, you can do these things. You can also add persistency to buffer ops, capability writes. So if you're doing capability reads and writes, I don't know how many of you are familiar with that set of research. All of these things are in there. And again, all of this can be made to work at any type of scale. We also have, for the people who just want to do regular writes, the ability to issue persistent flushes. So you may say, I want to do a lot of high performance writes, I get those across. Now I want to do kind of a checkpoint, if you will, persistent flush. When that comes back, all the writes, no matter what flavor they were, have now been ascertained as persistent or not. So you get a ability to checkpoint, which we've been told by various software people. They don't always want to do everything on a per write basis persistent because depending on your technology, it doesn't work well. So this flush was added in. One of the things that we wanted to be able to do, and this is a thing that we're emphasizing a lot, is eventually we want to get to this fully secured, fully composable infrastructure. That's our vision. So we want security everywhere. We want composability everywhere. And we've got a lot of stuff where we don't try to do load store across the data center. That's kind of silly. But with a rack or two load store, that's a 500 nanosecond worst case round trip for a lot of stuff. So we know we can do that fairly well, and that's where we focus. So now we can start composing systems, whether it's within a single box or a series of boxes within a rack or the rack next to you, and make that work fairly well. And in this regard, again, we can support a variety of topologies. There is support actually in there. I'm not going to talk about it much, but also that you can build RAID memory subsystems. If you look at the specs, all our stuff is public. There's this atomic fetch now that's in there that actually allows you to start building RAIDed memory in a very reliable fashion. So that's something else for this audience to consider. One of the things, I'm not going to talk about this a lot, but it's important, is how do we embody things? And a lot of people have focused on the DIMM today. The DIMM, if you're a mechanical person, and no offense to anybody who builds DIMMs, is a horrible form factor. Everybody will tell you that. It's a big problem for wiring up, cooling, provisioning. You make the trade-off. Someone was pointing out on the nanotube solution, you got to trade off from what you can do. So actually within the consortium, we built a series, and it's called the Gen-Z Scalable form factor, ZSFF, of form factors. And so you can see here in this DRAM example, we could support up to 280 gigabytes in a fairly small, about 3-inch form factor, and you don't have to put the most expensive DRAM in there. If you're doing SCM, you can scale this up to about 5 terabytes. And all of this stuff, the numbers I'm quoting here are with actual people's package numbers, package sites, et cetera, being explored. And then from a flash perspective, a single wide gets you about 48 terabytes. The connector that's been chosen is actually being adopted. We put it forward first, but it's now being adopted by multiple industry bodies. So now we can physically embody these things in much more interesting fashions and do it in a way that's very scalable. So like a 2U server in Flash could have a petabyte just sitting on its front plate. Okay? From an SCM perspective, that would be, say, a dozen modules, so 60 terabytes. I'm not sure anybody's going to pay for that, but we have the ability to now mix and match your Flash, your SCM, and your DRAM all on the same interconnect, all on the same physical infrastructure, and you can dial in now what your platform's going to do. So fairly straightforward. Doug asked us to talk about what have we accomplished, where we're going. So again, we've actually put a multi-vendor demo together. It was supposed to be at Flash Memory Summit. It was supposed to be the big coming out party. We ended up not being able to demo it. But at Supercomputing, we had a really good demo. We had about 10 vendors. We showed memory working. We showed shared memory in the sense that if you touch something on one screen, things appeared on the other screen. We were able to show switch topologies and that. So we actually did this all in FPGAs, and you can see some of the material on our website. Again, everything's public. So we have multiple specs out there that are public covering various aspects. We've got a lot of tutorials out there for educational material. There's a YouTube channel. Membership, I think, just a little bit over 50 companies now. We also have a free membership for academics and government research institutes. And we've had a couple of those now joining up. So we're expanding fairly nicely. What we're doing for this next year is we're going to focus on page-level data encryption and authentication because we want to make it to where eventually, if, let's say in 23, we decide to get rid of DDR entirely, because that actually is a point of attack, we just have co-packaged memory, it would be nice to be able to say the data is only in the clear within the processor itself, within that processor package. At all other times, it's always encrypted. So that's part of what we do in our architecture. We're actually going to be publishing a series of design guides covering all the different use cases that we've talked about in some white papers on it. We've got a new internal cable connector spec going to come out, and we're actually going to support 48-volt high power up to 1 kilowatt in our modules. So the new things that we're doing, we support a variety of existing mechanicals, but we have new mechanicals that'll scale up to the kilowatt. And so the guys doing accelerators, they're at 400 watts today. It seems insane, but there are people doing that today. Okay? And that was it. Thank you. I don't know if we have time, so.
Yeah, we have time for just a few questions. So any questions for this group?
I got to ask one. I'll ask it and maybe they can repeat it. Oh, thank you. So on the Gen Z, I mean, there's an awful lot of capability there.
Yep.
Can you talk about the software development work that's going on to get this into the operating systems and so we can take advantage of this wonderful hardware?
So there's, like I said, you can slide all this in with just system firmware changes, and you can make the logical PCI device and the memory work without any OS changes. That said, because their Linux guys keep telling me, stop saying no OS changes, we want to do interesting things. There is a software management work group that is working directly on this. Again, we don't need UEFI or ACPI changes, so they're working more on we've got all sorts of system firmware flows for mapping this stuff, and now they're looking at how do you do things like where do you position. There's also a lot of open source out there already for doing memory brokering, so if you want to do composability and assign portions of memory to a given system in that, there's actually open source demonstrated out there today. You send me email, I can get you the GitHub where it's at, but that's already available.
Other questions for any of the three? There's a question in the back there, and one in the front. Please address one of the speakers with your question.
Quick ones. One was that all the speakers were talking about coherent interconnects, right? And I know that the programming models are all coherent, so it's important to support it. But in practical applications, it's like the first thing we want to do is pin down the memory and do message passing on it, right? So to get the perf on it, especially if you start scaling, right? So it's like the first thing, if I used any one of those interconnects, I'd probably treat it as a message passing bus. So what support are you providing to communicate in that style?
I thought it would be.
So, no, you don't have to treat it as a message passing. In fact, again, all three can do, once you memory mapped it in, it's memory, it's load store, so you don't have to change anything. For Gen Z, we support a full paging service as well, so you can actually have components say, I'd like to page this in or out, and there are operations explicitly for page management, but you don't have to pin it, you don't have to treat it as message passing only. It's truly load store, different scales depending on the technology you're using. Okay?
One more.
I guess this is to all three of you. It seems like you're all doing kind of similar things. So why are you going to win, right?
The one thing, just the one reason.
I think there's a different focus for each. Gen Z has coherence, but I didn't really talk about it because we're trying to focus on, this is a memory conference, so I'm trying to focus on the memory aspects of it. So the way I view it is we've got a very broad set of applications and use cases we can support. You can dial in the features you want. It's a very versatile interconnect. It can support a variety of topologies. So I think because the potential TAM is larger in that regard, we should have a competitive edge. But I'll say he's got some stuff in product. That's great. Product was always good. He's got a demonstration vehicle. But I'll let you guys answer it. You know, there's different points.
I guess one thing we're doing is, yeah, we have a product and we have future products coming out, but our focus is around, we're really trying to focus on one specific aspect, which is tightly coupled devices. And I think there's, I think we like to think, we're in the Gen-Z consortium, IBM is, and so the switch network can certainly be compatible. So if we want a device that has very low latency, we think the only way to achieve that is with our specific protocol, but we're actually electrically compatible with Gen-Z and the 25 gig, and mechanically as well. So yeah, our memory form factor, we're now converged, from what I understand. The one,
portion of it.
the JEDEX, yeah. So there is some amount of compatibility where if you want to have high performance, low latency coherence, we can argue about coherence if you want.
Yeah.
But I think to do coherence, you really have to be close, but it's more from a latency perspective. But if you want to switch fabric, then we don't do a switch fabric, right? And so Gen-Z does. But I don't know about this guy.
You're asking for some contentions.
Yeah, he's looking for a contention, but I think they're different, like you said, different design space, architectural spaces. C6 is supposed to, if you think about it, scale up within the box or within the chassis or on the board to connect cards traditionally that have been DMA type devices. Yes, you could go outside there, but typically if you want to do a fabric, you'd either go like, typical clustering fabric like InfiniBand or Ethernet or Gen-Z or something that has that reliability and transport layer for that. So at different design spaces, I think they can coexist, meaning that if you want to go outside the box, you go one method. If you want to stay inside the box and do acceleration cache coherent thing, which was really hard to figure out how to interoperate on cache coherency, go C6.
Okay, thanks again, everyone.